Oh, it's gone. Okay, great. Thank you. So it's a real honor to present here. Actually, I was thinking today, this is actually the second time I presented. I initially presented on a study that Suncor did on energy efficiency back, I believe it was in 2011. So I don't know if what I did to come back, get invited again, but thank you. So definitely an honor here. So I'm going to talk today a little bit about the ESEIEH project that was also presented I think back in 2011, to give you a bit of an update as to how that technology and project is progressing, and also talk to what we see from an industry perspective on the potential for this technology. So I'm going the wrong way. There we go. So I think many people in the room are familiar, but I'll talk a little bit about what exactly the technology is and what we see the advantages are. Talk a little bit about the technology piloting and how we get from a concept through to commercialization. It's not a clean and linear process. It's very iterative, and I've been working on this project for quite a bit and seen it evolve a lot. So I'm going to talk a little bit about that. And then finally we'll talk about the next stages, steps to commercialization. So how do we take what we're learning in the field, and how do we actually lay out a pathway to deployment to take this from what looks like a good idea to actually making a significant difference, not only for Suncor, but also for the province in terms of reducing the cost of bitumen production, but also reducing environmental impacts as well. So a quick background, it's a mouthful of an acronym. It's Enhanced Solvent Extraction Incorporating Electromagnetic Heating. We call it ESEIEH. And it's not just one technology, but multiple technologies that we're bringing together to advance a brand new approach to extracting bitumen in situ reservoirs. So it basically combines a solvent extraction process with radio frequency heating into a full system that you can deploy for in situ reservoirs. And I'll talk a little bit more about the technology in a few slides later. But just to give you an idea of the status and what we've done, the original idea and patent was issued in 2007, or applied for in 2007, and so that moved forward into we called a mine phase test, and I've got a picture of that a little bit later, where we tested a 12.5 meter long antenna in our North Steep Bank mine. We actually you'll see the picture of it. We basically put a antenna horizontally into the mine to show that the RF heating could actually work in oil sands. And then what we're doing now, we're actually just starting up and going to proceed for the next 1.5 to 2 years, is a test at our Dover facility, where we're actually doing an in situ 100-meter long antenna along with the solvent process to demonstrate actually the entire process can work. So, number of advantages here. It's lower temperature. It doesn't use any steam, so you reduce greenhouse gas emissions. You reduce or eliminate all your water needs. And there's a whole bunch of, and also you reduce your capex and other advantages. So there's a whole bunch of advantages this technology offers over conventional SAGD if it's successful. And I think one of the things this project would not be successful without I think this is really a textbook example of how collaboration works. We were supported from the very start by the CCEMC and our partners at the Alberta Innovates Energy Environment Solutions. Really strong, technical and financial support on this project from the very start. And then also with our partners, Suncor as the host, but also Devon, CNOC Nexen, and Harris, our technology provider. I think all of the partners in this process have been critical for this success, and it's been a real pleasure to work with all these organizations. So I think everyone knows the challenges of SAGD. It's expensive, particularly in this cost environment, and also it's got significant emissions. So we recognize that technologies that can address multiple problems are really advantageous, and we see this technology as having that potential. So what is the ESEIEH process? A little bit more detail. So at a very high level, and let's see if I can get the mouse to work here. It's basically an AM radio antenna that's been put into the ground. So instead of, it's same configuration as a SAGD well, where you've got an injector and a producer well. The injector well it can inject both the solvent for the extraction process, but also acts as a dipole antenna. So it broadcasts RF energy into the reservoir. And so what this does is it actually heats polar molecules like water. Once the water vaporizes, it becomes transparent to the RF energy. So the RF energy can transmit quite a ways into the reservoir. And it can be, 5 to 10 meters into the reservoir. So a lot further than an inductive or a resistive heater could transmit heat. So as the reservoir heats up, you sort of get an initial desiccation along the length of the antenna. Then you can move into a solvent injection mode where you turn the heat down on the antenna and you start injecting solvent into the reservoir. And what this does is the solvent acts as a diluent, or it actually diffuses into the bitumen, modifies the viscosity, and you end up producing the bitumen much like you would in a SAGD well. So the advantage of this is, it doesn't use any water for the steam, and also it produces at much lower temperatures, or the 50 to 80 degree C range, rather than the 200 plus degree C range that you need for a SAGD production. So in terms of the technical details, as I mentioned before, the injector is repurposed as an antenna. So you have basically an RF transmission line that comes down into your reservoir, and then basically your well liner is turned into your antenna. And you've got a few other things you need to manage there. You've got some nitrogen gas, which acts as an insulator, so that you actually can transmit the energy down to the reservoir. You have fluid circulation, which is sort of usually like a dielectric fluid that keeps your tool cool. And there's a number of components around the design of the inlet-outlet barrier and a few other really unique components of this technology. And then your producer looks much like a conventional SAGD well. You've got usually an ESP or a PCP pump in the bottom of the well that's producing your fluids to surface. Now, some challenges because you're not producing a water bitumen emulsion, you're producing a bitumen solvent emulsion. So, in terms of sand control, in terms of pump operation, does pose some challenges, but those are challenges that we're working on and overcoming as we go forward. And so the antenna, as I mentioned, it's a dipole antenna, and you can see on the I guess on your right-hand side here, as you progress in your heating, what happens is your antenna, the heat starts right at the middle of the antenna, and as you dry out or desiccate your well bore, sort of a horizontal view, your heating spreads along that entire well length. And one of the really unique features of using RF heating for bitumen extraction is it decouples the heat delivery from the mass. So, for SAGD, for a steam-based process, or even a heated solvent, a vaporized solvent process, you're reliant on mass flow to get heat in your reservoir. What the RF technology does is it really decouples heating from mass flow. So you're able to tune, how much heating versus how much solvent you need in your reservoir quite precisely. One's not bound to the other. So that's a really unique feature of the technology. So what are the benefits? I mentioned, there's no water consumption other than, washing your hands at the control room, but there's no water involved in the process at all. And actually, since you actually end up producing some of the connate water associated with the bitumen, you actually end up producing water from this facility. So you could look at this, if you have it close to a SAGD facility, you could use that water as makeup water and reduce your freshwater intake. The greenhouse from Devon put together on what it does in terms of land disturbance. The main thing it does is it reduces the amount of metal you have at surface. So that also results in significant capex reduction. So you don't have your steam generators, you don't have your water treatment facilities. It really reduces your footprint and your capex. So, and I talk a little bit about, the capital expenditures go down, your operational expenditures, you don't have all of that water treatment. And that's a huge advantage, especially in this cost environment. And the last thing I'll talk about that we expect is a solvent process. I don't know if it's upgrading is the right term. I like to call it distillation. It actually leaves a portion of your asphaltenes in ground. So what you produce to surface actually is a higher quality bitumen. You know, typically, you know, the native bitumen might be 8 API. This will produce, let's say 12 to 16 API. So it significantly reduces the amount of diluent you need for your product to get it to market. So a whole bunch of advantages the technology offers. So here's this great diagram that Devin put together. So that's a conventional SAGD facility, and we looked at, okay, what would an ESEIEH type facility do to your surface facility? Well, it would eliminate those, and that's basically your water treatment, your boilers, your storage pond. So a huge advantage in terms of eliminating the amount of metal in the ground. I thought this was really powerful to say, like, you just take that out of the way when you go down the line with this technology. So a little bit of photos here. This was our North Steep Bank mine test, and you can see the yellow tube here is actually the well bore liner. So it's an RF transparent well bore liner. So we actually just pushed that straight in the front of the mine. I wasn't involved in the project this time, but I've been told that what happened is, we basically dug the project, our mine basically dug the project a hole in the ground. So they did their tests, and by the time they sort of looked up while they were through their tests, they realized they were then an island, and everything around them had been mined away. So they turned from a hole in the ground to an island. So they said, basically, you guys got to go. We got to mine this. So they got kicked off the site. So, anyways, it was really successful. You can see sort of some more of the equipment here, and basically what this test did is didn't include the solvent. It demonstrated that in fact the RF energy could be broadcast into the ore and could heat. And we saw very positive results. It's sort of a temperature profile with time. We saw very quick heating, and we saw it being able to be transmitted quite far into the reservoir. So that was exactly what we wanted to prove, that sort of de-risking the technology, prove that this core piece works, and then move on to the next piece. So the next piece was identifying somewhere that we could go to actually do an in situ test where we'd combine both the RF heating with the solvent process. And we identified Suncor's Dover site, which has the history of ESEIEH and the underground mining, underground in situ operations, and then piloting of SAGD. It made a lot of sense for us to repurpose that facility. And so we actually went to the old DOVAP site, and basically you can see this red box here. We basically put the ESEIEH well pair in between two of the original DOVAP wells. So great way to repurpose the land. We reused much of the equipment on the site and move forward on our test that way. So what are our objectives? We want to demonstrate first of all that we get bitumen drainage and production from electromagnetic heating and using a light hydrocarbon solvent. In this case, we're using propane. Measure some key economic indicators. So from our perspective, the key indicators we wanted to learn from this test were what's our production profile, what is our energy requirements, and what is our solvent holdup. So that's a big factor is, you're using solvent in your process, how much of that solvent is actually held up in your reservoir. And using all of that information to then, to calibrate a simulation model that we can go apply to commercial reservoirs. Piloting the ESEIEH hardware, both subsurface and at the surface, is critical. Better to find out the problems and the challenges with a small pilot than it is to go to a full field development. And we've learned a lot from this pilot so far. And then finally, determine project feasibility for the demonstration scale. So we look at, we've had a small scale mine phase. We've now done an integrated pilot. Our next scale will be to go to a demonstration scale. We'll look at 5 to 10 well pairs, and understanding the operational and technical challenges and solving those will help us apply that to the next demonstration scale. A few key pieces of technology that need to develop along the way. The first one is, we've got good reservoir models, but we had to couple reservoir modeling with electrical modeling. So one of the things that was developed as part of this is called Coupled Electromagnetic Reservoir Simulator, another acronym, CEMERS, which allows you to model your electromagnetic heating properties with your reservoir model, which really allows you to estimate your production levels and reservoir response. So our forecast for a pilot, the way that the sort of describes how the technology works. So what you do is you have an initial high power phase where it's several kilowatts per meter power density. You get the reservoir quite hot, desiccated, and it's a thermally dominated process. And then as you come down, so you get an initial bump of production, and then you basically you turn your antenna down into the sort of single kilowatt range per meter, and you start injecting your solvent. And so essentially it starts off as a thermally RF dominated process, and then as you go along, you're using the RF energy to sort of keep your reservoir at a constant temperature, and your solvent process dominates. And so the advantage, one of the advantages of this process is you continue heating your reservoir and you get a lot of your solvent. We're expecting a lot of your solvent will reflux and not get produced to surface. So you're kind of getting an in situ recycling of your solvent and not producing a whole lot of it to surface. Our expectation is, we're just in the startup phase. I don't have a lot of, data results to share with you right now because we're really in early days in the startup phase. But we expect it to run on the order of up to 2 years. And we're going to do a number of tests along the way to try and de-risk and understand how the technology responds in the reservoir. So to give you an idea, that's our facilities rendering, number of components. The major components that are unique to this system are, you have a surface transmission line that goes to your injector well. You have what we call the T-house, which is the transmission house, which converts the power line power into RF energy. And then you have what we call the D-house, which is right over here. And what that does is it's basically a dielectric fluid cooling system. So that's what keeps the whole system cool. But if you look at the totality of the plant, it's actually quite compact. And we also were dealing with repurposing an existing site. So it's not the most efficient layout because we're kind of using existing pieces. For a commercial embodiment, we expect it to be quite a compact site. So here's just some pictures from site, and this first picture here is, you can see, we call the inlet-outlet barrier and the well. This is the injector well, and you can see our transmission line, which goes back, our transmission house, and I'll call it our D house, our cooling house. And that's a better picture of the injector down here. And then here's a sort of a view, you're standing on top of the well, looking back, and probably recognize the superior yellow here. This is the propane bullet, and then you've got the rest of your processing facilities associated with your operations. And in the back, you can see some of the old AOSTRA buildings in the back there. So that's sort of, that's where we're at in the pilot. But I want to talk a little bit about one of the things I was asked to talk about was, how do we take this from this concept, this neat idea through implementation to actually making a significant difference, being a commercial a process that's actually a significant difference in the province. So another thing we have to work through from a producer's perspective is understanding the reservoir conditions and what the technology can and can't do. So that leads into understanding what our site selection, reservoir characteristics, and then also making sure this aligns with a overall growth strategy. And one of the things that gets quite iterative in this process is as you develop new technologies, your growth strategy changes because you might be going after other types of resources that you couldn't before. So that's something that is continually evolving. Facility design is the next thing we really need to think about. Because the technology has such a smaller footprint, and a lot of the equipment is actually based on the pad, you could move away from sort of a CPF-based, well pads with a big facility on the side, to something that can be more decentralized and more focused on your pad, which sort of leads to scale. You might be able to build these types of facilities at a smaller scale, go after a smaller resource, build them in a way that manages your capital expenditures on a more smaller bite-sized basis. So that's definitely an advantage. And then also modularity, the type of technology you might be able to actually bring a lot of the components to site as modules rather than building them on site. So that offers some pretty big advantages in the region. The other thing you have to think about is logistics. So typically you're looking at about on the range of about a megawatt per well pair. So if you're building a 40 or 50 or 60 well pair large scale facility, you're going to need a lot of power. So are you going to do that by on-site generation? Are you going to get it from the grid? So understanding how you're going to get power to site is important. Solvent becomes important. for any of these solvent processes, when you start getting to scale, you're going to need a lot of solvent, especially in the startup phase. And then you're going to have a lot of solvent to manage as you go from older to newer well pairs. So that's something you have to think about. Can you truck it? Are you going to pipeline it in? Where are you going to source it from? So that's all those logistic pieces you have to think of. And then finally, bitumen to market. And this is where you have call it an upgraded or higher value, lower viscosity oil. Are there things you could do on site? Are you going to use diluent? Could you do partial upgrading? Is this technology? I think there'd be less involved in upgrading this oil than a traditional oil sands oil. So a lot of these newer technologies may integrate really well with this, and this is some of the things we're starting to think about. And then finally, where are you going to source your diluent? Are some other things you can do around renewable diluents or other sources of diluent that might actually combine well to offer you an even lower GHG emission oil and more efficient down the line? So the next steps, we're going to complete this pilot. We've actually started and evaluating for commercial, the next demo scale. There is a lot of work that needs to be done in developing the RF equipment from the current pilot sort of, baling wire and duct tape approach to being something that you could reliably install on the ground and not worry about for 10 or 15 years. So there's a lot of work that's concurrently being done to commercialize the technology. And the next step will be really to go to that demo scale where you build out full well length, multiple well pairs, and we're really trying to be aggressive on that and getting that constructed and operated very early. Our goal is, before 2020, hopefully in 2018, get a commercial demo facility up and running. And then finally, once we really understand the performance from the commercial demo, we'll move into commercial replication scale in 2020. Now, this is important to keep in mind that this is one of multiple technologies that Suncor is working. We're working on a portfolio. I don't think that any one technology will be beneficial in every situation, but we see this one as having a lot of promise. So, we see this as all of this work is sort of a precursor to full deployment, and then and for new development, this being the prime technology that we'll go after. So just a final slide here. Just wanted to thank the CCMC and Alberta Innovates again, and all of our partners that have worked on this project. Again, I think this really has been a textbook example of how effective collaboration works. So, thank you.